All right, let's go ahead and get started. As I mentioned previously, this week the course is changing focus a bit. What we examined in the last 2 weeks, or last two projects, was thinking about how to use the idea of a search algorithm to implement an AI. And what we saw is that on one level, it was generally pretty effective. You know, we were able to create maze solvers. We were able to create successful checkers playing programs, at times, you know, fairly effective, I think is what many of you found. But what all of this had in common was the idea that as a programmer, you think through what's the human knowledge about the domain and how do I stuff that human knowledge into a program, you know, in an explicit way. You know, we had to think carefully about the specific knowledge we wished to encode. For example, when thinking about a board evaluation function, we would reflect on, according to the rules of checkers, you win by getting rid of all your opponent's pieces. So maybe a material difference where the bigger the gap is between our pieces, the better. You know, and what we do is some reasoning, some deductive reasoning from those principles to try to come up with an effective AI. And that approach has a lot of virtues. There's a lot to be said for the idea of not disregarding the human knowledge we have and not disregarding our ability to think carefully about stuff. When we looked at A*, part of the appeal and part of the power of A* is that we're coupling this human-specific knowledge, in the case of A*, with the heuristic estimator. We encode that knowledge and plug it into a very generic algorithm. And that is a lot of what makes that kind of generic search appealing as a form of AI. If you can just get the human knowledge into the computer somehow, from there, you just set the thing loose. You set loose the search algorithm and wonderful things happen. But it's not the only way to think about this stuff. And so for the next several weeks, our major focus is going to be on the idea of what's called machine learning. And so what's essential to the idea of machine learning is we come up with algorithms that essentially let us throw a bunch of data at the computer, and then the algorithm figures out from that data some deeper underlying idea without us having to, in some automatic way or some tedious way, write down what the algorithm ought to be. Machine learning comes in a number of different varieties, all three of which we're going to explore as we proceed. So those three major varieties are supervised learning. Given that there is supervised learning, you might guess that there is also unsupervised learning. And if you were to guess that, you would be correct. And then there's a third category, which is kind of orthogonal to these and works in somewhat different ways, known as reinforcement learning. We're going to spend the bulk of our time examining supervised learning, but we're going to have one project each in unsupervised and reinforcement learning. So you'll get at least a taste of all three major varieties and a feel for what kinds of algorithms we use for these sorts of things. We're going to spend the bulk of our time on supervised learning because in part, it's where most of the algorithms are. It's the type of learning that has attracted the largest amount of attention. And it follows from this that it turns out to be the type of learning that's yielded the most useful practical results. I'm not saying these haven't, they have, but supervised learning is what is used most in practice. Make no mistake, I am not denigrating these particular forms of learning. I have actually published papers in all three areas. So I've done research in all three types of machine learning. And for various reasons, I have an abiding fondness for each. But initially, we're going to focus on the idea of supervised learning. So that's what we're going to look at today. So today, what we're going to do is look at the overall concept of supervised learning. What is it? How is it structured? What does it involve? And having looked at the overall concept, we will explore two different algorithms for supervised learning, which are extremely simple to implement. And in part because of the simplicity of implementation and then the consequent simplicity of understanding just what it is the algorithm is doing, both of these actually get used quite a bit in practice. And I'll talk a bit about some examples of that as they come up. So, overall framework. What is the supervised learning problem? What problem are we trying to solve to which supervised learning is the solution? So, the overall problem is a problem of prediction. That is, given input data, we want to predict a category to which it belongs. So that's a pretty abstract idea. So let me make it a little more specific. For example, let's say you've got input data. So let's actually make a little table here. You've got some input data. What kind of classification might interest us? So let's say, for example, the input data is a handwriting sample. Classification we might want to predict is, what letter is it? And so this handwriting sample, you would imagine being encoded as an image, so basically a two-dimensional array of pixels. And that image gets thrown into some machine learning algorithm. And then the algorithm says something like, oh, that was a letter Q, for example, okay? And handwriting recognition will be something we explore starting in the next project, when we start looking at neural networks. So what might be something else that we try to classify? Here's another very famous example. The input data could be an email, and the classification could be spam versus not spam. So in other words, we have an email come in, essentially a string, right? And we ask our magic machine learning algorithm to tell us, is this spam? And if it is, it'll automatically throw it into your junk mail folder. In fact, one of the algorithms we're going to look at today sort of made its mark as a spam filtering algorithm. Okay, what might be something else? So related to the idea of a spam filter in that it's concerned with text is you can imagine the input is a comment of some kind, and the classification we're trying to make is a sentiment In other words, is this a comment where the person felt good saying it? Or was it a comment where the person felt bad? So a positive sentiment is the person feeling positive, good. This is a comment made in the context of being happy. A negative sentiment is something in the context of being angry or upset or some such thing. And this is a pretty useful and interesting idea as well. You can imagine having some kind of predictor that automatically picks these things out. This could be useful, for example, if you're a business that's got a product and they're trying to analyze user comments about the product and have some summary way of saying they liked it, they didn't like it. This is going to be our target domain for Project 3, is sentiment analysis. Here's another. And this is something that I'm actually actively working on at the moment. And that would be the input data is info about a student, and the classification is, are they on target to graduate? So I've actually been building a predictor using some machine learning algorithms that gets in various bits of information about a student and then makes a prediction about whether they're on target to graduate, with the idea being that if the prediction is suggesting trouble, that we then can marshal our resources to intervene on the student's behalf and help the student overcome whatever obstacles lie between the student and graduating. So that's actually something that I'm actively working on for Hendrix, like at this time, which is kind of cool. Here's another thing that I have that I continue to work on, which is the input data is something like a robot image. So in other words, an image being acquired by a robot. And we're trying to classify it in terms of the action the robot's supposed to take. So some image comes in and you want to predict, should you go left, should you go right, should you go straight? So I've done work in that context with imagining a human remote controlling the robot and the robot trying to learn to do what the human would do given an image. So that's been a lot of fun as well. So looking at stuff like this, we can see that the requirements for using supervised learning are pretty minimal, not non-existent exactly, but reasonably minimal. So here's what I mean. What we need to have is a data set where for each data item, what we have is some kind of input which is representable as a data structure. And if you look at all of these things, I think you can see in a straightforward way how we could represent them as data structures, right? So handwriting sample, robot image, two-dimensional array. That's the data structure. The email, the comment, string. Info about a student, that's basically just a fairly straightforward object with fields about different things, you know, grades and that kind of a thing. And, you know, so it's just kind of an object of some class, right? So you need input, and then for each input, you also need a label. And this is where the supervised part comes into play. So one way or another, one must construct a data set in which you have a large number of sample inputs. And for each of these sample inputs, you've associated a label, the category to which it belongs in terms of the categories that you're trying to predict. So obviously, attaching those labels could be labor intensive. It doesn't have to be, for example, though. For instance, in the sentiment analysis world, they've often done some astonishingly clever things. In particular, Twitter is well known for making its data available via a public API, right? Because there's basically just no privacy on Twitter. So, using the API, researchers have downloaded millions of tweets and assigned sentiment based on the emoji included in the tweets. So if a tweet doesn't have an emoji, it just throws it out. For every tweet with an emoji, it examines the type of emoji that it is, and if it's like a happy face or a thumbs up or any of the many kinds of happy emoji, that'll classify it as positive. And if it's the angry face or thumbs down or the other sort of I'm annoyed emoji, it'll classify it as negative. And so from that, they build data sets with millions upon millions of items that don't have to be hand labeled. With this imitation learning for a robot thing that we worked on, the labels are just what the human remote controller is instructing at a given moment. So if you picture the robot acquiring, say, 10 frames per second, and the human is constantly giving it commands, the command, in effect, as each frame is acquired, becomes the frame's label. Others are not so easy to automate. Handwriting sample is a bit tricky. There, you basically have to have a human that looks at the image and then marks it accordingly. That said, we have enormous data sets available for this, in part because a couple of decades ago, the US Post Office had very good reason to invest an extremely large amount of money on this. And for the most part at this point, handwritten envelopes have their addresses scanned automatically, digitally, and then the handwriting recognized straight from it. So with the spam versus not spam, repositories were fairly easy to develop based on kind of setting up an email program where people just sort of said, this is something I want to read, this is something I don't, as they looked at it. And so in a distributed way, it was possible to build some very powerful data sets. So make no mistake, labeling each item of input data is a major bottleneck in applying supervised learning. But A, there are often clever ways to get around this, and B, it can often be less work to do this than it would to come up with a handcrafted algorithm. Especially, so another way to do this sort of thing is like Amazon's Mechanical Turk platform, where you pay people small amounts of money to do small amounts of desk work. So you can imagine distributing a label task among a population in that way as well, if you've got some money to spend. So there are lots and lots of options here. But yeah, there's definitely some work involved. The beauty of this is once you've done the labeling work, effectively what you've done is to say, within the human mind is a concept or an idea. We have a large amount of data documenting what falls into one concept or another. The goal from there then is to build a data structure that is able to represent some kind of abstraction of the underlying idea so that it can be an effective predictor with stuff you haven't seen before. And that's what all supervised learning algorithms do. This semester, we're going to look at 2 this week, the neural network next week, the decision tree and the random forest sometime down the line. So I think we're going to look at about 4 of these. That'll give you different ideas of what these things are like and hopefully give you some sense of some of the pros and cons of different approaches. So I'm going to now talk a bit about what some of these algorithms actually look like. And then I'll conclude today by talking about how we do a performance assessment of these things. That turns out to be rather important when thinking about this stuff. Okay. So the first supervised learning algorithm we're going to look at is called K nearest neighbor. It's also known as KNN for short. K nearest neighbor. This is, in my opinion, the absolute dead simplest machine learning algorithm to implement. It can also be quite effective. I actually have a paper coming out in May that's based on some KNN algorithms. So still actively interesting, all kinds of stuff. It was a paper where I'm trying to find ways to make it more effective and more competitive with other approaches. So how does it work? KNN is pretty straightforward, but it is also a memory hog. It uses a lot of storage. And the reason it uses a lot of storage is this. It stores all training data explicitly. So the data structure for K nearest neighbor is basically a big giant array containing all of the labeled data. Okay, well, that doesn't seem terribly sophisticated. How do we get something out of it, right? So the key idea for K nearest neighbor is that we also have to define what we'll call a distance metric over the data. So in other words, we have to be able to take two different items of data and come up with a single number that talks about how similar they are. Or alternatively, what's abstractly speaking the distance between them. So for now, let's just grant that a distance metric exists, okay? We'll talk about what some of these look like in a moment. But given that a distance metric exists, the way we do a classification is apply that metric to our input versus all stored data. If that sounds like an expensive operation, that's because it is. Okay? So you've got to calculate a distance between your target input and all of the stored data. Then what you do is pick the K closest. Okay? So that kind of begs the question, what's a typical value for K? Well, for starters, a typical value for K will be an odd number, especially if we're doing just two categories, like with sentiment analysis. Why an odd number? It's because the K closest are going to vote. So whichever among those K closest, whichever label is the most common becomes the output of the algorithm. So let me review the algorithm. Again, this is really straightforward to implement, especially compared to stuff we're going to look at later, like neural networks, which are not straightforward, shall we say. You just store all labeled training data. That's what makes it a memory hog. Then, every time you want to do a classification, you apply your distance metric to compare your input versus each individual item of stored training data. You then pick the K closest. So a straightforward way to implement this is simply to sort them using that distance as a key. And if you sort them in ascending order, then the first k elements of the resulting sorted array will be your k nearest neighbors. Yes?
You say k must be an odd value?
Yeah.
Doesn't that mean it's like maybe 1 or 3 or 5 or 7? And why? I still don't get why.
Okay. Yeah. So typical values are 3, 5, 7, and 9. 1 is less common. But 3, 5, 7, and 9 are all fairly common values. So if we have two categories, so in other words, a sentiment can either be positive or negative. If we make it an odd number, when they vote, the result is unambiguous. So something can either be positive or negative. If I look at 3 samples, I can either have all 3 say positive, I can have 2 say positive, in which case I say it's positive, or I could have 2 say it's negative, or 3 say it's negative, in which case I spit out a negative. If I set k equal to 4, I could have a case where 2 say positive and 2 say negative, and that's ambiguous. Yes.
So k is basically a parameter that we're going to pass into the algorithm to tell it how many elements we want to pick?
Yep, that's right. Yeah, typically, so naturally your classifier is going to be an object, and so you would typically pass k in through the constructor. So as the object is initialized, you inform it, you are a 3 nearest neighbor or a 7 nearest neighbor, like that. So everybody with me so far? If everybody's with me up to here, I'll start talking about distance metrics. Okay. So distance metrics. On one level, this can really be anything you want, in the sense that whatever it is you come up with is usable by the algorithm. As long as it gives a distance between things that matches our human intuition about what's similar or what's different, you're in good shape. You then might be wondering, well, wouldn't that be really tricky to come up with? And you would be correct. So, in fact, this paper that I'm going to be presenting in May is entirely about distance metrics and some variations on distance metrics and assessing how they perform with k nearest neighbor. All of that said, you might be thinking, well, there's probably some standard issue stuff that people use. And you would also be correct. There is. So what's the standard issue thing to use? It depends on conceptualizing your data as a vector and here when I use the term vector, think linear algebra for those that have had it. It might just be the case that I keep referencing linear algebra ideas for like a while. But I'll explain exactly what you need to know from them as we go. This linear algebra is not a prerequisite for the class, but for anybody that's seen it, a lot of this is going to be pretty familiar. So what we mean by a vector is, in programming terms, really just an array. That is, you have to have a way of thinking about the data you're looking at as an array so that you can make numerical comparisons between them. What type of numerical comparison might we be thinking of? Well, imagine that you've got a vector that has 2 dimensions. In other words, 2 elements, or an array with 2 elements. That is to say, your inputs have 2 features. If it's an image, it's got 2 pixels, or what have you. So to think about the distance between them, what we might do if we've got 2 dimensions is just use the Pythagorean theorem, right? So if we've got 2 points, that is, we've got x1, y1, because this is just a 2-dimensional thing, and we've got x2, comma y2, and we're trying to think about how similar are these things. By finding the hypotenuse of a right triangle, that is a form of distance we might use or consider. And this is typically called the Euclidean distance. Why the Euclidean distance? Because Euclid and his elements gave us the Pythagorean theorem. Mathematical types who are really into stuff like real analysis might call this an L2 norm. Yeah. So just for your reference, So mathematically, it's just a matter of saying, well, if I can calculate the square root of x2 minus x1 squared plus y2 minus y1 squared, that could be my distance. It's not that big a jump from here then to imagine a vector that is n dimensional. And by n dimensional, I'm speaking mathematically. I'm not suggesting that you imagine that you're studying shapes in 500 dimensions, and trying to visualize some crazy geometrical thing, right? When we say n-dimensional, we're just talking about how many array elements do you need to represent the data. So if I have 20 by 20 images, we would consider that to be a 400-dimensional input, because each pixel is one dimension of the input space. If we're thinking about the idea of sentiment analysis, and we think, okay, I've got a sentence, I've got a tweet, I've got a review. How do I turn that into an array? The typical way that this is done is to use what's called a bag of words. So what do we mean by a bag of words? It is a histogram that counts word appearance. So note what happens when I use a representation like this. I'm just counting words. I'm not doing anything positional. I'm certainly not doing anything that would suggest grammar, at least not in English. Might be a different case in Russian. Pun intended for those familiar with Russian. It has what's called a case system where each noun is conjugated based on its role in a sentence. So German has this also, Latin, and so forth. English has vestiges of it with pronouns, So the subject pronoun for me might be he, but then if I'm an object of a sentence, I'm suddenly him. Or if I'm grabbing something, I'm suddenly his. So those are cases. So English originally had cases, and just over time it lost them, except for pronouns, where it kept them mysteriously. It's actually not that mysterious. Grammatical weirdness tends to be retained in languages for the most frequently used features. That's why we've got so many different forms of a verb like be, and then relatively few forms of a word like program. So anyway, so for pronouns, we actually hung on tenaciously to our declensions. For everything else, it just sort of went away. Bit of an aside, the idea of the bag of words then is you just build a word histogram. And you think about this and it's like, doesn't that throw away a lot of information? And you would be correct, it does. Oh well. Well, why is that not that big a deal? The reason it's not that big a deal is that on a practical level, using this representation, we can actually get some fairly interesting results. Then you might be wondering, well, given that it's throwing away information, wouldn't people be really, really, really curious to come up with other representations that don't throw it away? And once again, you'd be right. And people are studying that stuff avidly. But going with bag of words turns out to be good enough to get somewhere interesting, and has the additional virtue of being extremely easy to implement. Very easy to implement. Okay. So if you've got the bag of words, what your vector is that you're doing differences on It's just a count of the number of appearances of each word. So when you've got your string that's put into the bag of words representation, let's imagine a simple string like the fox is, oh, this isn't a good one because it doesn't have any repetition. Let's see. Yeah, you tend to need longer sentences to get there.
Not like green eggs and ham, or do not like them semi-ham.
There we go. Oh, let's go with that. So the bag of words representation is run : 2, forest : 1. So to calculate a Euclidean distance, and so we'll go with the green eggs and ham. I do not like green eggs and ham. I do not like them, Sam, I am. So this is going to have a somewhat larger bag of words, right? So we have I is to, do is to, not is to, like is to. But then, as you keep going, green is just 1, eggs is just 1, and so forth. So the Euclidean distance is just for each word, you subtract how many appearances did the word have in one document versus the other, and you square it, and then you add them all up. Now, you might be thinking, well, wait a minute. Not every word from every document is in every bag. What do? The answer is, if it's not explicitly represented, its value is 0. So if I'm comparing my eyes here to my eyes there, well, my difference is 2 minus 0, it's 2. So we add a 4 to my distance value. Now, something that also arises in this context is it turns out the whole idea of taking the square root becomes very optional very quickly. And the reason is square rooting is a relatively expensive operation. And if you don't square root any of them, you can just compare the raw values, because square rooting does not change the relative ordering you would get when you were to sort them. So it's actually really common with this stuff to not bother taking the square root. The importance of the square root in general is that it gets the units right. See, let's say x and y are in meters. If I subtract my x's and square it, I'm now in square meters. Same thing here. I've got square meters together, but if what I really want is meters, I need to take the square root. Doing these distances, it just doesn't really matter, because all that we care about is the relative ordering. And so it's pretty common to skip taking the square root. So that gets us our bag of words and our Euclidean distance. And so at this point, we have a machine learning algorithm. You might look at it and think, well, goodness, that didn't seem like super sophisticated, all these great claims are made and so forth. Truth be told, you can actually create a pretty decent handwriting recognizer doing this. And other stuff as well. With the handwriting recognizer, a little bit of image pre-processing is helpful. So they'll do things like find the centroids of the images and do some translations so that they overlap as much as possible, that kind of a thing. But yeah, fundamentally, this can actually work pretty well. And for your first cut at a data set that you're exploring, this can be a wonderful algorithm, especially because it is so easy to code. Yes?
So we're taking the distance from each thing in the first bag of words. Well, wait. Yeah, so each data set is just a bag of words, right?
Yeah. So every annotated training data, when it gets stored, is going to be stored as a bag of words, because that's all you really need to compare to. So you do that transformation, and then each time a new input comes in, you do the same transformation, and then you compare it against everything you stored. Like say you've got 1,000 training samples, which is pretty common. So you take your 1,000, you've stored them all, they're all bags of words. Every time you want to classify, you do distance measurements against all 1,000 items.
And do we sum up those distances, or how do we store those distances?
A parallel array can work, for instance. Like you might have an array where you group them into pairs of the object and the distance. And then you sort that array and then pick the first K. And then you do your voting and you've got it, you're done. So that's K nearest neighbor. Yes?
What is the element of learning from that algorithm? Like, what is learning?
In this case, learning is memorization. This learning algorithm is the kid who crams for the test with note cards. Right? So you go through, you memorize everything, you commit it all to memory, and then as things come in, you try to think about what's the closest example to what I've memorized for what I'm looking at. It may sound silly, but this actually has a legitimate cognitive basis in the brain. For example, let's say that in my life, I've seen a lot of chairs. So in my brain, I build up representations of different chairs I've seen in the cortex. This isn't strictly the same thing because in a way, the chairs are kind of getting averaged together in my brain. And that'll actually be a machine algorithm we look at 2 projects from now, doing the averaging process. But I fundamentally have a representation, multiple representations of chairs in my brain. I've got different ideas of the scope of what a chair could be that I've acquired through my memories of my experience. And then if I find that anything I'm looking at happens to look like a chair, aha, I'll call it a chair. Similarly, in a different part of my cortex, I've got a representation of tables. So as an image comes in and my brain's picking out pieces of it and comparing it to these reference ideas in the brain, there's going to be kind of a big winner. Now, what's a big difference between the brain and this algorithm? Big difference is that the brain doesn't have to take linear time to examine them. Right. The image can come into the brain, and the brain is wired with so many rich neural interconnections that it can simultaneously be considering all of these different possibilities. And so that actually makes it a lot more practical. So obviously the idea of monster machine learning algorithm, single core machine has been a long-standing problem in AI. In the last 10 years, what's become popular has been to jury-rig graphics cards to do AI work along these lines. So a graphics card is basically a parallel CPU because in parallel, it's rendering lots and lots of objects. It's doing the same computations on lots of different objects. So it turns out you can actually hack a GPU to instead process data structures like this to try to do some parallel processing and retrieval. Actually coding that is not only beyond the scope of this class, it tends to be beyond the scope of any particular individual. Like it takes a lot of work to hack a GPU. And so a lot of machine learning packages that are out there basically are APIs that'll then, you give it some data and it'll do all that hard work for you. But yeah, it's actually a real problem that gets at the core of a lot of what makes AI difficult, is that the human brain does massive parallel processing and actually fairly slowly. It's just so heavily parallelized that the fact that the calculations in the neurons are relatively slow doesn't really matter very much. Just because there are so many busy neurons going. Bit of an aside, but I think an important one. So yeah, that was a great question in a sense. What is it learning? I mean, that's basically it right there. Okay, so big problem with k-nearest neighbor, memory usage. This is sort of memorizing a bunch of stuff. What's really great about k-nearest neighbor is disregarding the fact that we do some pre-processing that disposes of information. It doesn't throw information away. That is, it's kept absolutely everything that you had. And so there's a role for every piece of information in that training set. So I'm going to show you now an algorithm that's the opposite extreme. It actually throws away a lot of data in the training process, but in exchange, it uses very little memory. This algorithm, which is historically the king of spam detection, is called the naive Bayesian classifier. It's called the naive Bayesian classifier. And we'll get at what each of those terms mean in a moment. I mean, classifier, I think you've got at this point. But naive and Bayesian, those terms are probably weird. So I'm actually going to talk a little bit in a bottom-up way about the naive Bayesian classifier so you can imagine what exactly it is that it's trying to do before we get into the calculations that it makes. So the fundamental idea of the naive Bayesian classifier is to use, the training data to build a probability model. Now, this is a pretty interesting idea. A lot of what the heart of this is to make observations from that training data, and basically by counting, it can build probability models. So what do I mean by this? Well, let's imagine the bag of words idea, okay? So if we think about this bag of words idea, we can think about trying to calculate something like this. What is the probability that a given word appears, perhaps with a given count? So the probability that a word appears given the classification that it was labeled with. More concretely, you might wonder something like, what's the probability that the word do appears given that it is classified as a Seuss, as a Dr. Seuss? Okay. And what's interesting about this idea is that it's actually fairly easy to calculate by counting. Again, you can use a histogram to just count how frequently does this happen. So, for example, we could say, look at the number of times green is in a Dr. Seuss. So something in this category. So we look at all instances, okay, of all documents in that category. And we just add up how many times did the word green appear. So if the word green appears 3 times in one document and 2 times in another, that's 5. Okay. So just across that whole category, how often do we have it? Yeah.
Is Dr. Seuss a novel, a book of some sort?
Oh, I'm sorry, Innocent. Yeah. So Green Eggs and Ham is a classic children's book.
Oh.
And Dr. Seuss was a children's author. Yeah. Right. Yeah, I just realized we dropped some context there. Yeah.
Oh, no, I was just, I have elbow right.
Stretching, okay. Right, yeah, so this is one of the most popular children's books in the United States. Green Eggs and Ham. It's silly rhyming poetry. I have read it aloud to my children probably over 1,000 times. If you add up all of their childhoods, which are ongoing, of course. Yeah. So Green Eggs and Ham is probably his best known book. It's for children's poetry considered something of a masterpiece. Yeah, it's actually pretty hilarious to read. In any event, we then divide this by the number of total words in the Dr. Seuss category. So if you add up the total number of words in all documents in that category, this is a way of saying, given that we're in that category, this is the probability of seeing that word. So as this input document comes into play, if that word appears, then that's the probability we're in that category. And that's the general idea of the naive Bayesian classifier. Now you might be wondering, well, what's so naive about this classifier? I'm about to tell you. What's naive about this classifier is that we don't really care what the probability of that word, of the word given the classification. What we really care about is the probability of the document given that classification. In other words, we need to have a way to calculate what does this value look like given all the words in the document. And here is the stunningly naive answer, which is at the heart of the simplicity of the classifier. The naivety is assume all P are independent. Now, assuming that every feature of your input is independent of every other feature is almost guaranteed to be wrong for any interesting data set. So why do this? The reason we do this is to make the calculation simple. It has the side effect of making the calculations essentially look like probabilistic heresy, as you'll soon see. Because if we assume that they're all independent, then what we can do is multiply for all words the probability of the word given the class. And then we just multiply them all, giving us really tiny floating point numbers. I have to admit that I personally find this algorithm extremely cringe-inducing because it starts talking about probabilities and then it combines them in ways that are not actually valid in probability theory. Oh well. Yeah, this is a really hacky algorithm. It has no mathematical elegance to speak of. But if you don't want spam, it's your friend. So you multiply all these values together, and that gives you some value. And as we just discussed, that value is really, really tiny. In fact, as we think about this scheme, we can see an immediate fatal flaw that would seem to condemn it outright. Namely, that if the probability of some word for that class turns out to be 0, you have successfully nuked the entire calculation. So, how do we deal with this completely fatal flaw, you might be wondering? The answer is we add 1 up here so that there's never a 0 in the numerator, because this is not hacky enough. And you add the total number of distinct words down here. Again, this just wasn't sufficiently hacky. Yes.
Total number of distinct words in the phrase you're trying to classify, or total number of distinct words in the category Seuss?
I think it's in the phrase you're classifying. I'll have to double check that. But yeah, it would be because you're just trying to counteract these ones. So it'll be the total number and what you're classifying. And there'll be at least one of them. Yeah. So with that handy little adjustment, obviously without that adjustment, this is going to be predicting zeros all over the place and it will not distinguish anything. I mean, to be blunt, I hate this algorithm, but it's very, very important and significant and often quite effective. I just keep thinking there's got to be a better way to combine probabilities that's actually got some mathematical sanity to it. Okay. So where do you go from here? Well, you do this for all classes. And then what do? Whatever yields the biggest product is the class. And bam, you've got a classifier. So we've seen that it's naive. We've seen that it's a classifier. How is it Bayesian? Okay. What does Bayesian even mean? What's called Bayes' rule looks something like this. So the probability, some classification for some data input is equal to the probability. So the probability, so you're given the data. This is what's called a conditional probability. The bar says to the right is what's called the prior. That is, this is something that's definitively known. It's a condition for the probability. And this is what's called the posterior. So this is the thing you're trying to find the probability of, given that that exists, okay? So the probability of being in a particular class given the data is equal to the probability of the data given the class multiplied by the probability of that class divided by probability of the data. Now, this is a rule in probability for finding conditional probabilities if you've got it going in the other direction. And so this captures the intuition behind this classifier, which is to say, if I've got a way of understanding what is the probability given a certain classification, given a certain category, I can go and I can count up how often I see some data. So I can derive this just by examining my input data. This term turns into a weight. In other words, if a particular class is rare, then that causes this value to be smaller. If a particular class is common, it causes the value to be bigger. This value turns out to be irrelevant because when we're trying to classify, we know what the data is. This value then is effectively 1. So we don't need it. So in the final classification, we actually don't just take the values themselves. We actually multiply the value by the number of, in that class, over the number of training items. So we actually have this weighting term here, depending on the frequency with which they appear. Intuitively speaking, it's a way of saying, in your training set, if there aren't many representatives of a class, you're going to penalize any attempt to use that classification, because from the training set, we know putatively that they are rare. So that's the philosophy behind this. And that, so, uses the intuition behind Bayes' rule. Putting it all together, we have the naive Bayesian classifier. Now this too is a very simple algorithm to implement. As you process each data item, you're really just adding up the counts that allow you to calculate these right there. So you're going to imagine essentially having a hash table where for each of these words coming in, you've got the counts for a given class. And so for each class, you might have a separate hash table. Okay. And then you just do the calculation with this little formula right here. So that's how your training data turns into a probabilistic representation that's usable by the classifier. Pretty cool. Like I said, I kind of hate this algorithm just because it just feels wrong. I feel unclean using it. But it's an extremely important algorithm and quite useful in practice. Cool. Any questions before we talk about how to assess a learner? Yeah, Mitchell. Oh, it's not really an absolute value. It's not unrelated. Using the 2 bars means magnitude. So it's just a way here of saying size of, or number of, yeah. Of words in the document that you're trying to classify. So yeah, so any other questions on the naive Bayesian classifier? It's very naive, but sometimes very effective. So unlike k-nearest neighbor, this is not a memory hog. It actually uses a relatively small amount of memory. And it tends to run fairly quickly. That is, k-nearest neighbor's running time is going to be dominated by the number of examples in your training set. With the naive Bayesian classifier, it's really just what are the number of distinct words in the bag of words. So you can have a 10 million item training set, and this is not going to run appreciably slower than a 10,000 item training set, whereas k-nearest neighbor certainly will. The disadvantage, of course, is this horrible, horrible assumption that the probabilities are independent. You can think of k-nearest neighbor as being the opposite extreme. That is, by storing all the data in the form in which it arrived, every examination of that data takes into account precisely where the features co-occur. This says that takes too much memory. Throw it all away, right? You could try to imagine something intermediate that directly calculates the conjoined probabilities by directly counting, well, how often did these 2 things occur together? How often did these 2 things occur together, and so forth? And you could make a somewhat less naive Bayesian classifier that way. I think in practice, it's not proven worth the effort or the memory space. So there we are. Cool. So you've now learned about 2 supervised learning algorithms, and these are fairly important ones. These are both still used in practice, in spite of the onslaught of the neural network. Any questions? We're ready to move on to the performance analysis. Let's talk performance analysis. So, performance analysis kind of stinks because if you use all of your data set to train it, there's a sense in which you can't use that same data to test it, right? To talk about whether a predictor is effective, you need to reserve some amount of your training data to tell you whether or not it's any good, right? So there are a number of approaches to this. The simplest approach is to do something like, say, an 80-20 split between train and test. Okay. So you set aside, say, 20% of the data to be test data. And then you see what it does. Now, having said that, what does it mean to test it? Here's the issue. There are 4 different outcomes we need to track. So, we have actual and what it predicts. And so then we have positive, and negative. So what are we talking about here? Your algorithm makes a positive or negative prediction for every test sample. When it makes a positive prediction, sometimes the actual will have also been positive, and that gives us a count in this corner. Sometimes actual is negative. So this is an example of a false positive. Sometimes it'll predict negative, but it'll actually be positive. That is a false negative. When it predicts positive and it's actually positive, and when it predicts negative and it's actually negative, those are good. So you want big numbers here and small numbers here. It's important to have big numbers in both of these places. For example, let's imagine that you have an unbalanced training set. 80% positive examples, 20% negative. And let's imagine that your algorithm learns everything's positive. So naively speaking, you'll say, oh, it's correct 80% of the time. That's wonderful. Except that all of those 80% are concentrated up here and none of them appear down here. And then you've got false positives all over the place. Why? Because it always predicts positive. So to understand the performance of these things, you have to construct this diagram, which is known as a confusion matrix. The confusion being on the part of the algorithm, not on part of the person examining it. So you've got a confusion matrix denoting these 4 possible outcomes. There's no magic number that says this is a good classifier or this is a bad classifier. All you can ever do is compare 2 classifiers against each other. That's one reason these 2 extremely simple algorithms are so important. If you do a first pass on a supervised learning problem with KNN and or naive Bayes, that provides a baseline that you can use for the classification accuracy of something more sophisticated you might also attempt to employ. So that actually gives you a way of posing the question, is all this extra machinery I threw into my neural network getting me anything? Is it getting me anywhere? Because these 2 algorithms are so simple, right, that they provide this just extremely important baseline. All right, so we have just a few minutes left, and I want to go briefly over your assignment for this project. So, oh no, I don't want the snipping tool. All right, so the assignment. I've got a zip file for you to download. It's got some things, and I'm going to give you a tour of it in IntelliJ in a moment. I want you to create a naive Bayesian classifier for this task. You've got a collection of sentences that have positive and negative labels, and we want to predict the sentiment of new sentences. And then we want to create a k-nearest neighbor classifier as well. I am providing you with a labeled collection of documents. I want each of you to go online and find a different labeled document set than this one. And I want you to try your algorithms on both of them. So part of what I think will be fun and interesting is when you all go off and find some different data sources, next Tuesday in your presentations, we'll be able to talk about what were some impacts on how the algorithms performed with some of these very different data sources that are out there. So you just Google for sentiment data, labeled sentiment data or something, and you'll find a number of options. So when you're going to go, I want you to find your own data set. So for Thursday, I would like you to talk about what other document collection have you classified. I want you to have attempted implementing at least one classifier for Thursday. And be ready to talk about the results you got from that one classifier. If you make a best effort attempt and it doesn't quite work, you can just be blunt about that and it won't be counted against you. But I really want you to make an effort to get one of these two working. It shouldn't be that hard to get one of them going if you've got a couple hours to spare for it. Because again, these are very straightforward to implement. So let me give you a very brief tour of the code and the data set. So the data set is present as sentiment labeled sentences. There are 3 different files. One is from the Internet Movie Database, one's from Amazon.com, and one is from some Yelp reviews. And there are 500 positive and 500 negative in each set. So what do these things actually look like? Well, let's glance at the Amazon set. So I try not to adjust the volume setting. To avoid that, I turn off the call button, which scrolls off the screen, which is situated just below the volume adjustment knob. So there is no way for me to plug it in here in the US unless I go by a converter. 0. That's a negative sentence. Good case, excellent value. That's a positive sentence. I thought Motorola made reliable products. Battery for Motorola Razr, great for the jawbone. That was positive. So a lot of these are fun to look at. What a waste of money and time. That turned out to be negative. And so forth. So that's what the data set looks like. I provided code to actually read in the data from the data set. So that's going to be in labeled words. There is from sentiment. You give it a file, and it'll actually turn it into a data structure that you can use. So what is it you're actually going to be doing? For every experiment that you run, you'll be writing a separate little main. And what you'll be doing in that main is telling it how do you want it tested. You'll be giving it a string array with all the file names you're going to use in the test, and then a function that grabs them from the file. So for the data set that I'm providing, that function will do the grabbing. And part of what you're going to be learning in this assignment is how to grab a previously unforeseen data set and actually build a way to process it so that you can generate the underlying data structure that you've got a chance to analyze. Because in practice, machine learning engineers have to do that stuff all the time. And data comes in a bewildering array of formats. So Bayes tester calls this simple tester test method. You give it the array of file names, the data reader, that function, and then you tell it to conduct the test, and you give it the constructor call for the thing you're testing. And then it takes the training and test values and goes from there. Within simple tester, it'll actually take your data set and break it into training and testing parts for you on your behalf. So we're almost out of time, so let me just get to some of the essentials. I provided a code skeleton for naive Bayes. So each of your classifiers is going to implement an interface called text learner with 2 methods. Train gives you a sentence and a label. And the label is just a string. So the sentence contains all the words that you're classifying. And then the classifier takes the sentence, does not have a label, and it spits back a string saying how it classified it. So when you're imagining k-nearest neighbor, for example, training is just going to stick it on a big array list of everything it's storing. Classify is going to traverse that array list, calculate the distances, sort it, and give you the best result of the modes. For naive Bayes, you're going to have to come up with a data structure to store the words and their counts for each category. just imagine hash tables. Like hash tables that maybe even contain hash tables. It might be a little saner to build some classes to wrap the hash tables, but I'll leave all that up to you. Right. So you build your implementation of naive Bayes, and then Bayes test 1 over here will test it. And when you test it, you just hit run. Of course, this is not going to work well since I didn't implement anything. But I want to familiarize you with the output format. So this one's split at 50-50. Training and test are equal sized. Test result is this. Its overall accuracy is 0%. Its positive accuracy is also 0%. And its negative accuracy is 0%. Using the accuracies for each label, you can build your confusion matrix. So it'll tell you how many were correct out of the total number. If you take that total number and subtract the other, then you get the other part of the confusion matrix, the inaccurate predictions. And that's basically the structure. So for getting started on the assignment, come up with a naive Bayes implementation, run Bayes tester and see how it does. By default, Bayes test 1. By default, it's going to do the IMDb data. So you might build some other test files that use Amazon or whatever, or Yelp. And then you might even do one that like puts all of them together into a single test using the string array. Yes?
In the sample data you showed us, it looked like the classification was always 0 or 1. Is that pretty standardized for any data set we would find, or are we going to need to deal with maybe data sets? And
you will have to deal with wackiness in the data sets. So what I did for labeled words was I created this from sentiment method, and you can just add static methods straight away for your other data set. Come back here. Okay, I'm going to close this. So basically, all this really did was processed each line until it figured out where the, what should we call it? The label was. Because some of the text went across multiple lines. And then it builds a sentence object, which is just a string array. Something that I did here was I created a banned words hash set to get rid of what we call noise words. So able, about, across, so I got a noise word list from somewhere of just stuff that's probably not going to tell you anything about sentiment. And then it just ignores those. And then it'll generate a histogram for that for you. There's a histogram class I'm providing. You might find that useful in implementing both algorithms. So that's the overall thing. Any quick questions? I've taken you over time. Sorry about that. All right, so for Thursday, identify a data set, try one of these implementations, see where you get. Each of you will talk about what you've done. We'll go back over some of this stuff in more detail as well, taking into account any questions you have. See you then.